Okay, so to conclude today's session, let me give you just a quick, numerical example which just sort of tells us, the properties of the discrete time Fourier transform. So basically, a numerical example to conclude our discussion today. We are given a sequence x of n, which has the following values: 2 times delta of n plus 2, minus delta of n plus 1, plus 3 times delta of n, minus delta of n minus 1, plus 2 times delta of n minus 2. Okay. So, what you have here is a example of a sequence which can be written in the following form: 2, minus 1, 3, minus 1, 2. Okay. And outside this window, it is zeros on both sides. You can write them zeros, or you can skip that. Okay. So notice that this is a sequence that is real valued. It is non-causal and it has even symmetry. X of n is the same as x of minus n, even symmetry. Okay. Again, some things for you to note. Okay. Now, the problem that we have, the task at hand is, without evaluating x e of j omega. That means you cannot write down or compute the expression without evaluating x e of j omega. Obtain the following answers. Obtain the following. Okay, so we don't compute, not allowed to compute x e of j omega, but without that we still want to compute the following. The first one is x e of j 0. Okay, this is the same as x e of j omega with omega equal to 0. So if you look at the expression that you have, n equal to minus infinity to infinity, x of n e power minus j omega n, if you set omega equal to 0, what will you get? You will get summation over n equal to minus infinity to infinity, the sum of x of n. E power minus j omega n will become 1. So, this will be equal. So, it will be 2 minus plus minus 1, 2 minus 1 plus 3 minus 1 plus 2, the answer equal to 5. X e of j omega is equal to 5. Okay. Next one. What is phi x of omega? What is the phase response of the discrete time Fourier transform? Okay. Now, here is where the aspects of looking at the fact that it is even symmetry. Okay. If you go back and look at the a real valued sequence which is even, what is its discrete time Fourier transform? It will be real valued. Okay. How do you verify that? Let's write down the expression. So, just though we are not allowed to calculate, we are just going to look at what is this expression. X e of j omega is going to be equal to 3 plus, next term is minus e power minus j omega plus 2 e power minus j 2 omega. Then the two terms on the other side, minus e power plus j omega plus 2 e power j 2 omega. Okay. So, when you add these together, you get 3 minus 2 times cosine omega plus 4 times cosine 2 omega, because e power j 2 omega plus e power minus j 2 omega, that's 2 times cosine 2 omega. So, notice that this is an expression which is real. So, x e of j omega is real valued. So, if you see a real valued sequence that has even symmetry, then the Fourier transform is going to be real valued and therefore, the phase is going to be 0. So, a sequence that is real valued and having even symmetry always will have 0 phase. So, this is the definition of what is called a 0 phase sequence. The discrete time Fourier transform, if you look at its phase, will be 0 because the discrete time Fourier transform is only is real valued. Okay, just a couple of more interesting. The third one, integral minus pi to pi x e of j omega d omega. What is this equal to? How do we calculate that? So, look at the expression for x of n. It is 1 by 2 pi integral minus pi to pi x e of j omega e power j omega n d omega. Okay? If you substitute n equal to 0, x of 0, what do you get? 1 over 2 pi integral minus pi to pi x e of j omega d omega.
That's exactly what we have. So what will this be equal to? Just the only thing to be careful about is don't forget that 1 over 2 pi. So this will be equal to 2 pi times x of 0. What is x of 0 is 3. So this is equal to 6 pi. Okay? And last two, x e of j omega at omega equal to pi. Okay, this is equal to summation k equal to minus infinity to infinity x of k e power minus j omega. I'm going to put it as pi k. Okay. Now what is that equal to? This is going to be equal to summation k equal to minus infinity to infinity. E power j pi is minus 1. So basically what you will get is minus 1 raised to the power k x of k. Okay, so whatever is the value of k, correspondingly you get a minus a plus. So this is going to be equal to, for our sequence, it's going to be 2 minus 1 raised to the power of minus 2. Then this one is going to be minus 1 raised to the power, so this is going to be, again, it's going to come out as plus 1. Then plus 3, plus 1, plus 2. Okay, so this is equal to 9. So this xe of j pi is equal to 9. And the last one that I would like you to do is Parseval's theorem. Okay, integral minus pi to pi xe of j omega magnitude squared d omega. Okay, remember that if you had a 1 over 2 pi on this side, this will be equal to summation k n equal to minus infinity to infinity of mod x of n magnitude squared. So if you have only this portion, if you have only this, then what you will get is equal to 2 pi times the square sequence. 4 plus 1 plus 9 plus 1 plus 4. That is equal to 38 pi. Don't forget this 2 pi, again very, very important, because it is there in the overall expression. You then should get this equal to. Okay, so let us summarize what we have looked at today. So today we have looked at primarily understanding the properties of the discrete time Fourier transform and the different the applications. Some of the important applications, the property of linearity, time shift, how to do a frequency shift, how to do when you do convolution in the time domain, and it results in a multiplication in the frequency domain. Multiplication in time produces for you convolution in frequency. So these are the properties that we can use quite extensively in applying the discrete time Fourier transform as a very powerful tool. So remember that we have derived the symmetry properties and in the last class we have also looked at the symmetry property, and in this class we looked at the transform properties, and in the next class we are going to be looking at some standard Fourier transform pairs. This is given in table 2.3 in Oppenheim and Schaefer. Most of these, in fact, we have already looked at what delta n is. Delta of n minus n naught, we have already looked at. When you have a DC term, how you'll get these Dirac deltas. So all of these we have already looked at, a power n u of n. So again, there are many things that we have already looked at up to this point. So when we meet next time, we will start from property number 5 and then look at what are some of these results. Basically, it will be using the discrete time Fourier transform theorems and the symmetry properties. Okay, so we will stop here and we will pick it up from here in the next class and build on it and make sure that we have a very good handle on discrete time Fourier transform. Thank you.